Welcome to our deep dive into polymorphism in C++. Today, we'll unravel what polymorphism really means, why it's a cornerstone of object-oriented programming, and how it empowers your code to be more flexible and powerful. Whether you're new to C++ or brushing up on advanced concepts, understanding polymorphism is essential for writing robust, maintainable software. We'll start with the basics, explore real-life analogies, and then move into hands-on coding examples. By the end, you'll see how polymorphism allows a single interface to represent different underlying forms, making your program smarter and more adaptable. Polymorphism at its core means many forms. In programming, it refers to the ability of a single function, operator, or object to behave differently in different contexts. Imagine a person who is a father, a husband, and an employee all at once. Depending on the situation, he exhibits different behaviors. Similarly, in C++, polymorphism lets you write code that can work with objects of different types through a common interface. This concept is not just theoretical, it's a practical tool that helps you build scalable and reusable code. Make the idea of polymorphism more relatable, let's revisit our earlier analogy. Think about a man who is a father at home, a husband to his spouse, and an employee at work. He adapts his behavior based on the role he's playing at any given moment. In C++, objects can also adapt their behavior depending on how they're used, thanks to polymorphism. This flexibility is what makes object-oriented programming so powerful and versatile. Polymorphism is one of the most important features of object-oriented programming. It allows you to write code that is more general and abstract, reducing duplication and making maintenance easier. With polymorphism, you can design systems where new types can be added with minimal changes to existing code. This leads to software that is easier to extend and adapt as requirements evolve. C++ polymorphism is mainly divided into two types: compile-time polymorphism and runtime polymorphism. Each type has its own unique mechanisms and use cases. Compile-time polymorphism is achieved through function overloading and operator overloading, while runtime polymorphism is achieved through function overriding using virtual functions. Understanding the distinction between these two is key to mastering polymorphism in C++. Let's start with compile-time polymorphism. This type is resolved during the compilation of your program. It's achieved through function overloading and operator overloading. With compile-time polymorphism, the compiler determines which function or operator to invoke based on the arguments provided. This leads to faster execution since the decision is made before the program runs. Function overloading allows you to have multiple functions with the same name but different parameters. The compiler decides which function to call based on the number and type of arguments. This makes your code more readable and organized, as related operations can share the same function name. For example, you might have a function called add that works with both integers and doubles depending on what you pass in. Let's look at a practical example of function overloading in C++. Imagine a class with three functions named func. One takes an integer, another takes a double, and the third takes two integers. When you call func with different arguments, the compiler automatically picks the right version. This is a classic demonstration of compile-time polymorphism in action. Here's a simple C++ program that demonstrates function overloading. We define a class with three versions of the func method. Depending on whether you pass an int, a double, or two ints, the corresponding function is called. This shows how the same function name can perform different tasks based on input, making your code both flexible and intuitive. When you run the function overloading example, you'll see different outputs depending on the arguments. For instance, calling func7 prints the value of x as 7, prints the value as 9.132, and func8564 prints both values. This demonstrates how compile-time polymorphism lets a single function name adapt to various situations. Operator overloading is another form of compile-time polymorphism. In C++, you can redefine how operators like plus or work for your custom classes. For example, you can make the plus operator add two complex numbers or concatenate two strings. This makes your classes behave more like built-in types, improving usability and readability. See operator overloading in action. Imagine a class representing complex numbers. By overloading the plus operator, you can add two complex numbers just like you add integers. The operator function handles the addition of both real and imaginary parts, making the code clean and intuitive. This is a powerful feature that brings your custom types closer to native types in C++. When you run the operator overloading example, adding two complex numbers like 10 plus 5i and 2 plus 4i results in 12 plus 9i. The overloaded plus operator makes this possible, showing how you can extend the language's capabilities to fit your needs. This is another great example of compile-time polymorphism in C++. Now let's move on to runtime polymorphism. Unlike compile-time polymorphism, which is resolved during compilation, runtime polymorphism is determined while the program is running. This is achieved through function overriding, where a derived class provides its own implementation of a function defined in its base class. The decision of which function to call is made at runtime, allowing for more dynamic and flexible behavior. Function overriding occurs when a derived class defines a function with the same name and signature as one in its base class. When you call this function through a base class pointer or reference, the derived class's version is executed. This is the essence of runtime polymorphism, enabling your code to choose the correct function implementation based on the actual object type at runtime. Consider a base class with a virtual function called print. The derived class overrides this function with its own implementation. When you use a base class pointer to call print, the derived class's version runs. This demonstrates how runtime polymorphism lets your code adapt dynamically depending on the actual object being referenced. Virtual functions are the key to enabling runtime polymorphism in C++. By declaring a function as virtual in the base class, you tell the compiler to use late binding. This means the function to call is determined at runtime based on the actual object type. Virtual functions are essential for building flexible and extensible class hierarchies. Let's look at a code example. We have a base class with a virtual function print and a non-virtual function show. The derived class overrides print. When you call print through a base class pointer pointing to a derived object, the derived version is executed. However, calling show always invokes the base class version since it's not virtual. This highlights the difference between virtual and non-virtual functions. Running the virtual function example, you'll see that print outputs print derived class, while show outputs show base class. This is because print is virtual and resolved at runtime while show is resolved at compile time. This distinction is crucial for understanding how polymorphism works in C++. Polymorphism relies on class hierarchies and inheritance. When you have a base class and several derived classes, you can use pointers or references to the base class to interact with objects of any derived type. This allows you to write code that is both generic and extensible, as new derived classes can be added without changing existing code. It's important to note that virtual function calls are not allowed in constructors. This is because the object is not fully constructed yet, and calling a virtual function could lead to unexpected behavior. Objects in C++ are built from the ground up, so virtual calls are only safe after construction is complete. Key feature of runtime polymorphism is using a base class pointer to refer to a derived class object. When you call a virtual function through this pointer, the derived class's version is executed. This allows your code to work with objects of different types in a uniform way, making it easier to manage complex systems. When you call a non-virtual function through a base class pointer, the base class version is always called. This is known as static linkage, where the function to call is determined at compile time. In contrast, virtual functions use dynamic linkage, where the decision is made at runtime. Understanding this difference is crucial for mastering polymorphism. See what happens when you don't use virtual functions. Suppose you have a base class shape and derived classes square and rectangle. If you call the getArea function through a base class pointer, the base class version is always called even if the pointer points to a derived object. This is because the function call is resolved at compile time, demonstrating static linkage. Running the example without virtual functions, you'll notice that the base class's getArea function is called for both square and rectangle objects. This is not the desired behavior, as we want the derived class's version to run. This limitation is why virtual functions are so important in C++. Now let's see how virtual functions solve this problem. By declaring calculate as a virtual function in the base class and overriding it in derived classes, you ensure that the correct version is called at runtime. This allows you to calculate the area of different shapes using the same interface, demonstrating the power of runtime polymorphism. In the virtual function example, the base class shape declares a virtual calculate method. The derived classes rectangle and square override this method to provide their own area calculations. When you call calculate through a base class pointer, the correct derived class method is executed, giving you the expected results for each shape. When you run the virtual function area example, you'll be prompted to enter dimensions for a rectangle and a square. The program then calculates and displays the area for each shape using the correct method. This shows how virtual functions enable dynamic behavior based on the actual object type. Sometimes, you want to declare a virtual function in a base class without providing an implementation. This is called a pure virtual function. It forces derived classes to provide their own implementation, making the base class abstract. Pure virtual functions are essential for defining interfaces in C++. To declare a pure virtual function, use the syntax virtual int area equals 0 in your base class. This tells the compiler that the function has no body and must be implemented by derived classes. Any class with at least one pure virtual function becomes an abstract class and cannot be instantiated directly. Abstract class in C++ is a class that contains at least one pure virtual function. You cannot create objects of an abstract class directly. Instead, you use it as a base for other classes, ensuring that certain functions are always implemented in derived classes. This is a powerful way to define interfaces and enforce design contracts. Virtual functions allow you to create a list of base class pointers and call methods of any derived class without knowing the specific type. This makes your code more flexible and extensible, as you can add new derived classes without changing existing code. It's a key feature for building scalable and maintainable software. Let's revisit the class hierarchy concept. Imagine a base class fruit with derived classes like citrus and non-citrus. Further, citrus can have lemon and orange, while non-citrus can have banana and apple. This hierarchy shows how generalization and specialization work together, and how polymorphism lets you interact with all these types through a common interface. Our fruit hierarchy, fruit is the most general class, while lemon, orange, banana, and apple are more specific. Citrus and non-citrus are intermediate levels. This structure allows you to write code that operates on the general fruit type but behaves differently depending on the specific fruit object. This is a practical example of polymorphism in action. Polymorphism is widely used in real-world applications. For example, in graphics software, you might have a base class shape with derived classes like circle, rectangle, and triangle. You can store all shapes in a single list and call draw on each, letting polymorphism handle the details. This approach simplifies code and enhances flexibility. One of the biggest advantages of polymorphism is how easily you can extend your systems. If you need to add a new shape or fruit type, you simply create a new derived class. The rest of your code, which works with base class pointers or references, continues to function without modification. This makes your software future-proof and adaptable. Polymorphism also makes code maintenance easier. By centralizing common behavior in base classes and customizing specifics in derived classes, you reduce duplication and make updates simpler. If you need to change how a function works for all types, you can do so in the base class or override it in specific derived classes as needed. In large software projects, polymorphism is invaluable. It allows teams to work independently on different parts of the system, knowing that their components will integrate smoothly through common interfaces. This modular approach leads to better collaboration, easier testing, and more reliable software. While polymorphism is powerful, it's important to use it correctly. Forgetting to declare a function as virtual in the base class can lead to unexpected behavior. Also, be careful with object lifetimes and destructors. Always declare destructors as virtual in base classes to avoid memory leaks when deleting derived objects through base pointers. Make the most of polymorphism, follow best practices. Always use virtual functions for behavior that should vary in derived classes, prefer abstract base classes for interfaces, and use smart pointers to manage object lifetimes. These habits will help you write safer, more maintainable C++ code. Let's recap what we've learned. Polymorphism allows objects to take many forms, enabling flexible and reusable code. In C++, it comes in two main types: compile-time function and operator overloading, and runtime virtual functions and overriding. Using polymorphism, you can write code that is both general and adaptable, making your programs easier to maintain and extend. Polymorphism isn't just for textbooks, it's a practical tool you'll use in everyday coding. Whether you're building user interfaces, processing data, or designing games, polymorphism helps you manage complexity and write cleaner code. The more you practice, the more natural it will become to leverage polymorphism in your projects. To deepen your understanding of polymorphism and C++, explore additional resources like online tutorials, documentation, and coding challenges. Practice by implementing your own class hierarchies and experimenting with both compile-time and runtime polymorphism. The more you code, the more confident you'll become. Polymorphism is a foundational concept in C++ and object-oriented programming. By mastering it, you unlock the ability to write code that is flexible, reusable, and easy to maintain. Remember to use virtual functions, understand the difference between compile-time and runtime polymorphism, and always follow best practices. With these skills, you'll be well equipped to tackle any programming challenge. Now that you've learned the essentials of polymorphism in C++, it's time to put your knowledge into practice. Try building your own class hierarchies, experiment with function and operator overloading, and implement virtual functions in your projects. The more you apply these concepts, the more natural they'll become. Happy coding!